I will be talking about how to separate information and communication complexity, but mostly I will be talking about how we cannot separate information or communication complexity, so that might be a better title. And this is joint work with Laila Fontes, Rahul Jain, Sophie Laplante, my student Mathieu Laurière, Jérémy Roland from ICALP. And I will also talking about some previous work with a subset of these authors and David Xiao from a couple of years ago. Okay, so I guess most people of you know what is communication complexity. Let me just go briefly through these things. We have two parties, Alice and Bob. They receive some inputs, X and Y, and they want to jointly compute some function. For example, is X equal to Y, or is X bigger than Y, or anything you can imagine, okay? And what we want to do is that we want to compute this by minimizing the amount of communication between Alice and Bob, okay? So this is a well-known model. It has been studied in many different areas of computer science, mostly because it relates to other things like circuits and VLSI design and streaming algorithms. So whenever you want to prove a lower bound on something like memory or a data structure, many times you reduce the problem to communication complexity problem, and then you prove lower bounds for the communication complexity problems, okay? Okay, so what exactly is the complexity that we're counting? So one of the things we can try to count is how many bits go from Alice to Bob, okay? But as we are here in an information theory workshop, maybe sometimes the bits that go between Alice and Bob do not contain any information. So if I always send the bit 0, I'm sending a 0, but Bob already knows that it's a 0, so the information content of this message is 0. So there are two things that we can try to count. One is how many bits have to go between Alice and Bob, and the second would be some sort of idea of how much information does Alice and Bob exchange between them, okay, about their inputs. So let's see one example where you can see that these two things may be very far apart from each other. So let's imagine that we want to have a protocol which is a randomized protocol. We allow Alice and Bob to have random coins, but we want them to always be correct, okay? And they want to solve equality. It's a very simple problem, X and Y. How can I solve this problem? Well, one of the ways would be for Alice to pick a random full rank matrix, n by n matrix. Let's say X and Y are n-bit strings. And then I just multiply X with my matrix, with the first row of my matrix, and I send the outcome to Bob, okay? Bob checks whether m.x is the same as m.y. If it is the same, then he tells Alice, okay, it's the same, send me the next one, the second row. It's the same, send me the other one. At the moment where Bob will find that something is different, he will say, okay, our inputs are different, so we can stop the protocol, okay? So how many bits do we have to communicate on average for this protocol? If X and Y are different, then by picking a random matrix on expectation, in very few steps, we will figure out that the two strings X and Y are different. So I'm only going to send a constant number of bits if I want a constant probability of success, right? But what happens when X and Y are the same? Well, Alice will have to send all of mx to Bob, which means that she will have to communicate n bits, okay? So let's say that the distribution on X and Y is that with half probability they're equal, with half probability they're different, which means that with half probability the communication will be constant, with half probability it will be n, so the communication overall will be omega n, okay? Now, how much information does Alice convey to Bob through this protocol? So again, when X is not equal to Y, then there are only a constant number of bits that go from Alice and Bob. So the information cannot be more than constant because the communication is constant, okay? But how much information does Alice send to Bob when actually X and Y are the same? This is the only tricky point. Well, what does Bob learn at the end of this protocol? He learned one bit of information, which is that Alice's input is the same as Bob's input, right? So in case they are not equal, he learns a constant number of bits because very soon they will stop the protocol. In case they are equal, the protocol will go all the way to the end, but the only thing that Bob learns that he didn't know is that x is equal to y, which is one bit of information about Alice's input, okay? So even though to solve this problem I need to communicate roughly n bits or n over 2 bits of communication, the real information that goes between Alice and Bob is only constant, okay? So we can see in this case that there is a gap between how many bits we need to communicate and how much information we are actually sending through this communication, okay? So now that this gap exists because I told you that I need to have 0 error in this protocol. If I can allow an epsilon error, then I can also make this communication to be constant, okay? Okay, so the main question we were trying to understand is how this information versus communication differs in interactive protocols. And before that, I need to define exactly what I mean by the information. The communication is kind of obvious, is how many bits you count the bits, okay? So what would I mean by information complexity of a protocol or of a function? So let's say again we have Alice and Bob, they receive some inputs and they have some random coins and I fix some protocol pi, okay? And I also fix a distribution over the inputs, some distribution mu. So then I want to see x, y, and pi as the random variables that correspond to the inputs x and y and to the whole transcript of the protocol, okay? So this is a random variable that depends on x and y and also on the coins that they might use during the protocol. Okay? So the way I define the information complexity of a protocol is just by the mutual information of x and pi given y plus the mutual information of y and pi given x. So what are these two terms? This term is just how much Bob learns about x given the transcript from the transcript of the protocol, given what he knew in the beginning, which is y, okay? And this term is how much Alice, who knows x, learns about Bob's input, which is y, through this communication between Alice and Bob from this protocol, okay? So this is how I count the information content of the protocol, okay? All right, on the other hand, the communication cost of the protocol is just the maximum number of bits that Alice and Bob have to communicate over all inputs and random coins. And then if I want to go and talk about the function, then I just optimize overall protocols. So I look, give me the best protocol that solves f, that means that it computes f with high probability, of the information cost of this protocol, okay? So it's this definition, but I optimize, I find the protocol that minimizes this information cost, okay? And this would be the information cost of the function. Again, this is over a fixed distribution mu, and I can go and say, what if I care about the worst distribution? Then I can optimize also overall distributions, and then I get what we call information complexity of the function, which is a non-distributional notion, okay? So I have the protocol, the function given a distribution, and just the function, okay? Okay. So let me just go back and recast the question that I want to ask in a more information theoretic notion so that even the information theory people understand what I'm saying, because it's very simple. So we all know the source coding theory by Shannon. If you have a source of entropy, of some entropy of x, I can encode this source using basically entropy of x number of bits, okay? But this result is in the asymptotic, meaning that you can, if you amortize the cost of how many bits you want to send, and you take the limit, this is exactly the entropy of x, okay? If you want to do it though once, which is what I call a one-shot or single-shot communication, then we can use the Huffman encodings, and you can again do it with entropy of x plus 1 bit, okay? So the gap between what I can do in the asymptotic case and what I can do in the single-shot case is just a plus 1, okay? So this is why we say that basically when we have a single message that Alice wants to transmit to Bob, then we know how to compress. We know how to compress the communication into its information content, which here is the entropy, okay? We lose 1, it's okay. Okay, so this is what we know. What we would like to understand is what happens when we have two-way communication. So we have messages back and forth between Alice and Bob. At the end, they have to compute this function. And here I want to ask the same question. What happens with the communication and the information? Can I compress the communication of Alice and Bob, of this interaction between Alice and Bob, into its information content? Okay? And again, I can ask the question in the asymptotic sense or in the one-shot case. Okay. Okay, so here are the two, oops, still works. So here are the two conjectures that we had maybe a few years ago. So what does it mean that they can compress? It will mean that the randomized complexity of f given any mu is roughly the same as the information content. Okay? So it's going to be some order of this information cost of the function. Okay? And then there is a weaker conjecture which says that I don't necessarily care if you can do it for every distribution mu, but I only care if you do it about the distribution that maximizes the complexity of this function. So if I look at just the randomized communication complexity of the function, which is the worst case overall distribution, is this roughly the same as the information complexity of the function? Again, this is the worst overall distributions. Okay? Maybe this is true without this necessarily being true. Maybe we don't know how to compress for every single distribution, but when we look at the hard distributions for the problems, then we know how to compress. Okay? So conjecture 2 will be, somehow weaker than conjecture 1. Why would we care about this? Well, in one hand, it's a very fundamental question when it comes to information theory. Can you compress a dialogue between two people? You know how to compress a single message. Can we compress a whole interaction? But it's also interesting because it has some applications that we kind of use mostly in computer science, which is the direct sum property. And the direct sum property says that if I want to solve k instances of a problem, then the resources I need should be k times the resources I need to solve one instance of the problem. So this is the question. If some measure has a direct sum property, it means that if I want to solve k instances, then I need k times the resources. Okay? And we know that this is true for this information complexity. Okay? And if information would be the same as communication, then we would prove the same for the communication complexity, which is something that we don't know. We know that it holds in some specific cases, but we don't know in general that for all functions you have this property that if you want to solve k instances of the function, you need k times the communication of solving one instance. Okay? And these are a couple of things that we know. There's a paper by Braverman and Anup, who's here, that shows that in the asymptotic case, then we do know how to compress. Okay? So the information cost of the function is the amortized communication complexity. It means that if you have a large number of instances of the function that you need to solve and you take the limit to infinity, that indeed you can compress exactly to the information content. Okay? So this is kind of the analog of the Shannon entropy for the Shannon theorem for one message. Even if you have a whole interaction in the asymptotic, you can perfectly compress it. Okay? So what remains to show or to see is whether this actually can hold in the single shot case where you just have an input and you want to output the function, okay? Which is the case of communication complexity. Usually in communication complexity, you want to say what is the communication complexity for a given x and y, not what happens if you want to solve the function many times. Okay? So one thing we know is that the communication cannot be more than exponential in the IC, okay? But the question is, can we do something better here? Okay, so, oh, I think I went the wrong way. So, all right. So if we want to show the compression, we need to find the compression scheme. But if we want to show that these two things are actually not equal, then we need to find a way to separate between them, right? And how can we find a way to separate between them? It means that we have to find some notion that lower bounds the communication, but kind of upper bounds the information. We need to find something which is in between somehow, between this communication and information. So finding lower bounds for communication complexity has been something that people have been doing for many, many years. And there are many different lower bound techniques. Okay? So there are things that have to do with rectangles, with discrepancy, with partition bounds. I don't want to get into this, but the reason we have so many different techniques are also because when we are studying different problems, then at some point the techniques are not strong enough to get a tight bound for a problem, so you have to come up with a new technique. And then you can solve this problem, and then more and more. So for all these different problems, you had to use different techniques, but note that nothing goes above this smooth rectangle. So we don't know anything that we can prove using these stronger lower bounds. The higher you are in this picture, the stronger you are, right? We don't know any function that you cannot prove a tight lower bound with smooth rectangle. Okay, we didn't know, but we knew how to solve it only with the things above, okay? All right, so this is what was happening before information complexity, and then information complexity arrived. This is also a lower bound for communication because the number of bits, the amount of information you can transmit is not more than the number of bits you are sending, okay? So we know that this information complexity is smaller than communication, that's fine. What we try to understand is how low or how close to communication it can be. And one of the ways to try to understand this is to relate this with all the other kind of lower bound techniques that we already had. Okay? So the first result of this form was by Breverman and Weinstein that showed that at least the information complexity is bigger than this discrepancy. So any lower bound for communication that was going through this discrepancy bound, it also automatically gives the same lower bound for the information complexity. So you cannot use this discrepancy to separate the communication versus the information complexity, okay? Because they're both bigger. And what we showed the year after is that basically the information kind of subsumes not only discrepancy, but pretty much everything we knew as a lower bound technique for communication complexity, apart from this partition bound. But okay, I'll tell you a little bit more about it afterwards. But somehow this shows that nothing that was proven using these methods can actually separate these two things. Okay? And as I said, most of the functions, most of the natural functions that we had studied before, you can't get a tight bound using these kind of techniques. So basically for most of the lower bounds that we had already, the lower bound was not only for the communication, but also for the information complexity. Okay? Okay. So this was the theorem that we proved, that this information complexity is bigger than this relaxed partition. I kind of told you a little bit this. This means that all lower bounds for communication complexity that they had, they also lower bound the information complexity. This means that for all these functions, you do have some sort of direct sum. We also proved something for gap Hamming that Robbie also talked about this thing. Okay, so I want to give, when do I finish?
60 minutes.
60 minutes, okay. So I want to give you a very short flavor of how we proved this lower bound and then go to the relative discrepancy, which is the second part of the talk. The reason is because I think this is kind of an interesting way of looking at all these lower bound techniques. So you can write linear programs for all these lower bound techniques. It's not very clear what kind of intuition you get out of these linear programs. But what we did here is we gave some sort of operational meaning of what these lower bounds mean. And what I mean is the following. We defined what we call the zero communication protocols as a means to study communication complexity. So this is kind of an oxymoron in the sense that we want to study how much Alice and Bob need to communicate in order to solve a problem. And here I'm defining something where Alice and Bob are not allowed to communicate. Okay? And I'm claiming that studying these zero communication protocols will tell us something interesting about the communication. Okay? So what do I mean? So here is a simple thing that Alice and Bob can do. Imagine that there is a protocol P that solves some function with error epsilon using C bits of communication. Okay? Then I claim that there is a way for Alice and Bob to not communicate at all. Okay? And then for every input, either they're going to abort with some probability, and this probability is 2 to the minus C, or if they don't abort, then the error that they will have is exactly the same as the error they had in the communication protocol, epsilon. Okay? So can you see how we can do this? So imagine that this is my protocol. I used some coins and I was communicating, and then Bob would output F with some very good probability. Here I want to do the same by saying that, okay, Alice and Bob are not allowed to communicate at all, okay? But I allow them to abort, okay? So what are they going to do? What they're going to do is that basically they're going to look at the randomness. They're going to look at the first C bits of the randomness. And Alice is going to check whether her input X is consistent with the C bits, okay? So Alice would say, okay, if I look at the first C bits of randomness, is this a consistent transcript that could have happened with Bob, given that my input is X? Are these valid messages that I could have sent, okay? And Bob basically does the same. He looks at the same C bits of the transcript and says, are these bits consistent with me having Y and Alice having something that I don't know, okay? And if both of them decide that the transcript is consistent, then they say, okay, and they output according to this transcript, okay? If not, then they abort, okay? So what is the probability that they abort? Well, once you fix your coins, your transcript was C bits. There is one transcript which is consistent for both. So the probability that you hit this transcript is 2 to the minus C, okay? So it's quite easy to see that this abort probability will always be at least 2 to the minus C, okay? All right. The question is, can you do better? Okay, maybe there is a better way of doing it than just looking at the first C bits of transcript and saying, is this consistent or not, okay? So I can define this notion of efficiency of the zero communication protocol, so which is exactly the probability that Alice and Bob do not abort, okay? So I'm defining this notion. I'm saying, okay, here is a measure of how hard this function is, okay? How much efficiency can I have in a zero communication protocol says that with that probability, I'm not going to abort. And if I don't abort, then I'm almost always correct output, and I output the function f. Okay? Okay, so we defined this efficiency. And what we showed basically is that the efficiency you can achieve is not just 2 to the minus c, but it's actually something better, which is 2 to the minus information complexity of the function. Okay? So how well you can create a zero communication protocol does not depend on the complexity of the communication complexity of the function, but on the information complexity of the function. So we showed that this eta here is always bigger than 2 to the minus information complexity, which gives you this lower bound that information complexity of a function is at least the log of this 1 over eta, this efficiency. Okay? And why is this interesting? Is because this efficiency you can actually very easily see that is exactly the same as this relaxed partition bound. Okay? So this kind of gives you an operational meaning of what this relaxed partition means, and actually the partition as well. The difference is just whether here you put almost equal to eta or exactly equal to eta. This is the difference between the two. So you can see at this partition bound, which is kind of the strongest lower bound for communication complexity, in an operational way, which is give me a zero communication protocol and try to optimize the non-aborting probability. And this non-aborting probability will tell you exactly the same as this linear program somehow. Okay? And what we showed is that this information is actually bigger than all this linear program that also subsumes all the things below. Okay? So maybe, okay, I skip the compression, but okay, you can ask me offline how we went from 2 to the minus complex communication to 2 to the minus information. Okay, so this is what we knew in 2012. We knew that this IC is pretty high on the compared to the other lower bound techniques. But of course, there is a continuation to this story. The continuation is that there was a paper by Ganor, Kohl, and Raz, which kind of changed things, because what they did is that they actually showed an exponential gap between IC and CC. What do I mean by that? They fixed the distribution mu and some Boolean function f. This function is called the bursting noise function. And they provided a new lower bound technique called the relative discrepancy, okay? And they basically showed that this relative discrepancy is between the CC and IC. And what they computed is that the IC for this function, according to this distribution, mu is actually log 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 n, where n is the size of the input, okay? While the communication of the function, according to this distribution, is log log n, okay? So one way to see it is that there is an exponential, there is a function and a distribution for which there is an exponential gap between the information complexity and the communication complexity. So if we go back to our conjecture, can the randomized or the distributional communication complexity be roughly the same as information complexity? This result shows that no, okay? So we have to come up with a new conjecture because we still want them to be.
So it could be so that even on the one-way case, in the one-shot compression, you have this little one dangling bit.
Yes.
So it could be just saying that you maybe have log log again or log log.
Yes, thank you. So here is my new conjecture. You can either say that R and communication information are exponentially far apart because you do have a gap. You can also say that you must lose something. For one message, you lost one. For interactive case, you could lose up to log log n, even log n. This will still be okay with this result. Now, there is another reason why maybe this log n can appear, which is not just because it will, not contradict the previous example, but basically the way you can try to hide information is by using your private coins. Like if we don't have private coins, then we kind of know how to compress. But the fact that I have some private coins that the other party doesn't know, it means that later on maybe I can open some things that we need in order to solve the function, but not everything. So this is what we don't know how to compress, protocols that use private coins. But again, this log n also appears, it's not the same thing, but when you want to go from private coins to public coins, then again, you can use Newman's theorem and you still get this log n additive factor on how to use public coins from private coins. But okay, so I don't know if this is relevant or not, but at least we know that they cannot be roughly the same. You do have an exponential gap when you go to the very, very small regime. And I guess the main question is, can you actually prove an exponential gap between n and log n? That would actually show that they are exponentially different. Okay, before that, this proved that we have to change somehow our first conjecture, which is what happens for fixed mu. What about the second conjecture, which is, can we prove a gap in the non-distributional case? Because this is what we care about the function, we care about the worst distribution, okay? Okay, so what we showed in last year, we wanted to understand if this relative discrepancy, which is this new lower bound technique that Ganor et al. Proposed, if we can actually use it to separate IC and CC in the non-distributional case, okay? And what we showed is actually that this is not possible. Why? Because if you go to the non-distributional case, then this R disk is lower than this relaxed partition bound, which is lower than IC. So there's no way you can use this to separate IC and CC, because it's smaller than both, okay? And it's actually not very difficult to do it. What we had to do is that we had to stare at this relative discrepancy for quite long to understand what it means. And because we didn't really understand what it means, we said, okay, let's recast it as a linear program. So we found the linear program that is equivalent to this. So now you can start dealing with linear programs. And once you have a linear program, then this is also another linear program. You look at the linear programs, you do a change of variables, and you see that one is smaller than the other. Okay? If you know what is discrepancy, discrepancy kind of says how small rectangles do I have to separate my matrix so that the rectangles are all almost monochromatic. If you don't know, it doesn't matter. So here what you do is not only do I have to care about how small the rectangles are given this distribution mu, but you can kind of try to cheat by changing this distribution a little bit. You can take some weight from rectangles that are very, very balanced, then put it to other ones that were not so balanced to make them more balanced. So somehow you have one more extra freedom to play than with discrepancy, which is you can tweak a little bit the distribution on the inputs. But OK, it's not very important, but because it's not obvious. But OK. All right. So as I said, what we showed is that this relative discrepancy is smaller than the relaxed partition. So you cannot use it to separate these things. We also managed to understand a little bit better if you fix mu, what happens. So all these kind of things here are linear programs. Okay, we have this CC and IC. What we did in the first paper is to show that this CC is bigger than this linear program. This linear program comes from the partition bound if you add one extra constraint. So this is a linear program. If you add this extra constraint, then you go here, which we knew what to do. The relative discrepancy is basically starting from the same linear program, but adding a different constraint. Okay? So that's why this thing and this thing are not comparable, because you just add a different constraint to the same linear program. And then if you add both constraints, then you go to this weaker version, right? So this is either you can go this way or this way. It's this linear program plus these two constraints. And the weird thing that happens is that in the distributional case, this thing here and this can be exponentially different. This is why our disk was log n, and this guy was log n. But if you optimize overall mu's, then these two things collapse and become the same, which means that the relative discrepancy is the same as this, which is smaller than this. So somehow, there's not much intuition there apart from you write down the linear programs, and if you start adding constraints, you see what happens, and you see what is smaller than the other. Okay? Okay. Oh. So I just want to very briefly show about there is another type of lower bounds which are very, very strong. And the reason they are very, very strong is because they don't deal with rectangles, but they deal with partitions. So this thing was called public coin partition bound, and was proposed by Jane, Lee, and Vishnoi in 2014. And they kind of showed that it's actually very close to CC. It can be only, they are quadratically related, these two. Okay? And then again in the same paper of Ganor, Cole, and Raz, there was another proposal for another even stronger lower bound, which they called adaptive relative discrepancy, which was also somewhere, we didn't know where it was, but what we show it does is basically exactly the same as this public coin partition bound, which means that they're all related to communication. It also means that they're extremely difficult to use in practice because we have no idea how to deal with partitions and not rectangles. So we do have lower bounds which are very good compared to CC, but they are not very useful, to be honest. Okay. Okay, so let me just in 1 minute recap what I said. Our first question was to try to understand what happens when we fix a distribution for the input, what happens between the communication complexity of the function and the information complexity. So at some point we showed that almost all lower bound techniques are smaller than IC, which means that we cannot use any of these to separate these two things, which means that they should be close. This was the idea. But then there was the Ganor, Cole, Ran paper, and then there is kind of a simpler version for a different function by Rao and Sinha that showed that there are examples where the IC could be triply logarithmic in the input size, while the communication is only doubly logarithmic in the input size. So again, the question remains, does this mean that there is some additive loss or some multiplicative loss of log n, or does it really mean that we can get an exponential separation between these two, between n and log n, for example, or square root n and log n? And this is what happens if we go to the non-distributional case. Okay? So what we showed is that this relative discrepancy cannot separate information and communication. But then, of course, there is a reply that Ganor, Cole, and Raz again, they had a follow-up paper where they actually show, well, there is an equal and a log missing here. They can show the same separation, but now in the non-distributional case. So even in the non-distributional case, you can get a separation between log-log and log-log somehow. So even here, we need to modify somehow this conjecture. At least there will be some loss that depends on n. Okay? All right, so here is some open problems. I guess the main question, I said it already, is can we get a separation between information and communication that is between the input size and logarithmic on the input size? Then this partition bound is a little, we tried very hard to show whether it is above information complexity or below information complexity, and it's still not very clear what's happening. And one last interesting point is that if you look at the protocols that have very small information complexity, they're really terrible when it comes to communication. So the protocol that has this log information complexity has exponentially worse communication than the best communication protocol. So somehow it seems that if we really want to hide something, we need to pay it in communication. We don't have a protocol which is the best possible in communication and the best possible in information. Okay? And the question is, can we see a little bit better what happens with this, with a trade-off between the information and communication? Okay? Okay, sorry, that's it. Thanks.